Okay, so let's start our astroparticle physics session. Please have a seat. Am I amplified? You got this? Yeah, okay. So our first speaker will be Dr. Hyun-Soo Lee, speaking about dark matter searches.
Okay, so I'm it's my great pleasure to be here to discuss about the direct detection of dark matter. I'm Hyun-Soo Lee on Center for Underground Physics in Institute for Basic Science. Let me clarify my talk first, because there are a lot of particle dark matter candidates with many order of magnitude different mass and cross sections. So my talk just focus on the weakly interacting massive particle and definitely direct detections and experiment. So I cannot cover all of interesting experiments, definitely. Only a few selected topics that actually discussed in this ISAP conference or listened to conference as well. I really apologize if I missed your favorite experiment. And also, I apologize I do not cover the right dark matter and directional search. They are equally important, but I didn't have time. So let me start the current status as a recent PDG result. I would like to categorize 3 items. That is, the first one is the high mass region. There are quite comparative between the liquid xenon experiment. And a couple of experiments are searching for low mass dark matter. And then there are unresolved items, the Dama Libra. So this is basically all my talks. Let me start with the high mass region. They are really well progressed. We reached to about 10 to the minus 46 at 50 GeV. In this PDG, actually, this was already outdated, but this is amazing progress. I think we are following the so-called dark matter Morse law, which means our sensitivity is exponentially improved as a function of time. So during last 5 years, 20 years, about 5 order of magnitude improvement was happened. So current best limit is actually given by, from 2007, the liquid xenon dual phase TPC gave best result. So let me briefly mention about the principle of liquid dual phase TPC. When particles interact, the primary scintillation was happened together with the electrons. So electron was drifted with the high voltage supplied, and then when this electron meet the gas, and then it was amplified. So then you can imagine the primary scintillation and secondary drifted electron signal with the time difference due to the drifting time. One of the extremely advantage of this type of detector is the particle identifications. So the WIMP-like nuclear recoil events to the electron most background events has different S1 to S2 ratios. So then, as you can see here, quite clear separation between the nuclear recoil signal to electron recoil are achieved even for very low energy regions. That brings up one can design something almost background free experiment. There are actually happen to up to the tone scale experiment nowadays. So most recent and world best result in high mass region was given by Xenon 1 ton. That was just 2 months ago. They used the 1 ton year data and then obtained the 4 times 10 to the minus 47 at 30 GeV WIMP mass. This is already 2 times factor 2 better limit compared to the latest PDG result. They are moving really fast, and they plan to have an N-ton detector in just next year. How it is possible is all shielding and infrastructure just reused. Only the inner shell that can be replaced with the N-ton vessel just to accommodate the more liquid xenon. So they want to start the N-ton experiment in next year. One of the competitors for xenon N-ton is the Lux Zeppelin experiment. We're running in the South Dakota in USA. One of the special design is they have an outer detector based on the gadolinium loaded liquid scintillator. So then this is just outside of liquid genome vessel. So then effective volume of or fiducial volume of genome can be enlarged. So more efficient use of liquid genome is possible. So they are going on time actually as their schedules. So Christ already delivered for liquid genome, and PMT assembly is ongoing. And also the large portion of liquid genome was already delivered in the underground. So the others are already contracted. So in this year, all liquid genome will be delivered. So they are trying to operate physics run early 2020. Another proposed experiment is the Panda X photon experiment in China Jinping. And they said the assembly and commissioning will start next year. So then probably 2020 or 2021, we're going to have about 3 of independent liquid genome experiments. XMAS is a single-phase liquid genome experiment running more than 4.5 years. And because this is a single phase, they didn't have a particle identification. So using the spectral shape, they tried to extract a WIMP and then set the new limit was reported here. And then also they do the updated analysis of annual modulation. And this is basically slightly negative modulation, but basically consistent with the 0 and much lower than what Dama observed. There are 2 ongoing liquid argon experiments. The DEEP used the 3.6 ton single-phase argon detector, but in this case, they can do the particle identification using the pulse-shape discrimination for somewhat higher energy regions. And dark side used the dual-phase experiment with about 50 kilogram. And they basically have a different running time, but they didn't have any signal in their region of interest. And then at the limit, there are basically compatible between this deep and dark side limit. So the liquid argon group has a different plan. Instead of competing, they make just a single very large detector in near futures. So all 4 running experiments are agreed to make the so-called dark side 20K experiment in near futures. So that corresponding to 50 ton of low background underground argon detector. This eventually will move to the 300 ton detectors. So sensitivity was given here. So LGN, Genome, and ton has some comparative projected sensitivity, while the dark side will cover the even higher mass region in near future. If this LG and Genome and ton make reach to their sensitivity in 2022, then this Moore's law can be continued at such a time. So following this is not quite simple, right? I mean, this is not just increasing the detector volume. We also should reduce the background in same amount of, that basically means between the 20 years ago, our background is 5 order of magnitude reduced. This is amazing succeed in this field. Okay, so let me move to the low mass dark matter search. That actually have a pretty different approach. I mean, in this case, we need a lower energy threshold detector instead of a higher mass case. I mean, the higher mass is always better, low background, but the low energy threshold pushing this region to be even lower mass region. So dark side 50, I already mentioned for high mass region, but they also provide a very interesting analysis. In this case, they use the S2 only signal. S2 means the drifted electron. So electrons are basically amplified. So then the energy threshold compared to the S1 with the S2 is much low. So however, because they didn't have S1, then PSD was not possible. So spectral shape are used in their WIMP extraction, and then they set the world best limit between the 2 to 6 GB WIMP mass. CREST actually low temperature calorimeter detector with the calcium tungstate crystals. This case has pretty good particle identification based on the heat and light ratio. So in this experiment actually have a really opposite direction of the high mass case. I mean, their previous experiment used a 300 gram detector, but now use the 25 gram. Main purpose is reducing the threshold that obtained about factor 3 improvement, and also with the crystal growing by themselves, the background has been improved. So with the about factor 25 lower exposure, they achieved the comparative result in low mass region, and below 800 MeV, much stringent limit are obtained with the CREST 3. CDEX used the high purity germanium detector. CDEX 10 obtained the 103 kilogram days data, and they obtained the best limit in 4 to 6 GB at the time, but it was actually covered by PICO already, and dark side 50 already. So they plan to go into the tone scale detector. Their basic plan is they're growing the germanium detector by themselves, especially in underground Jinping. So then background can be well controlled, and then they provide the very impressed sensitivity. USG used the gaseous spherical proportional detector. So in this case, with the low mass target gas and then low enough energy threshold, they provide the world best limit below 600 MeV region. They will try to reduce this energy threshold, understanding this excess. So near future, even lower mass are possible. I should mention the PICO. This is not the low mass dark matter search, but they provide the world best limit in spin-dependent WIMP proton cross sections. PICO 60 used the C3F8 bubble chamber, and as you can see, and this experiment actually improved their limit more than order of magnitude compared to the previous experiment. And they plan to have a next phase, PICO 500 in the future. Okay, so let me move to the final item, the unresolved DAMA signals. The DAMA used the 250 kilogram of low background sodium iodide crystal and studied the annual modulation of event rate in low energy regions, and they found the quite clear modulation signature. As you can see here, this is a residual spectrum in 2 to 6 kV. And now in 0.3 sigma significance was observed. And they provide the modulation amplitude as a function of energy. And this modulation amplitude spectrum, as well as the phase of this modulation, are quite well matched with the known dark matter model that we typically use in the most of experimental interpretation. So then one can easily interpret this signal into the WIMP Euclidean spin-independent cross-section parameter space. So this is the WIMP sodium interaction case, and this is WIMP iodine interaction cases. This is not the end. Recently, just a couple of months ago, DAMA released the new phase 2 results that are corresponding to the 6 additional year modulations. Basically, they see the similar modulation, and one remarkable improvement is the threshold was reduced into the 1 kV. And just summing the all 13 years modulation, they obtain quite clean modulation with the 13 sigma significance. This is an amazing number. And then the comparison between the phase 1 and phase 2 is here. So phase 2 reduced their energy threshold. Below 2 kV, they are quite interesting, but they have a mild increase. This brings some attention because just in our typical dark matter model, below 2 kV should be sensitive for iodine interaction. So then one can easily imagine that the large increase because this rate is A square dependence. So then expected shape is like this, but the DAMA modulation is here. And high mass case also not compatible. So this paper authors are claim that the DAMA Libra phase 2 are not compatible with the typical spin-independent WIMP Euclidean interactions. However, if we bring some way to suppress the iodine, such as the isospin violating model or spin-dependent cases, still this is possible to be dark matter cases. Also, a long-standing argument is here. So these authors actually used some known radioisotope of gamma that are actually unclear, but based on their understanding, they made a simulation, and then this simulation seems to be covered most of gamma total events. So to have the modulation to be matched with the typical model, here we should have about 0.3 in this parameter, in this range, should have it in the 2 kb region, but it seems not available such remained data. So this makes something confusing situation. Anyway, the independent sodium experiments are highly required to clean up all this issue. This brings up the large effort of sodium iodide in worldwide. And 2 experiments actually start the physics run already. Anice already take about 11 months of data, and cosine in Korea Yangyang Underground Laboratory, we took about 22 months of data. So cosine 100 gave impressed result. Just using the 2 months of initial data, they do the spectral fit based on the good understanding of background. And then the limit obtained here are basically ruling out the gamma region, but this is gamma phase 1's interpretation into the spin-independent WIMP Euclidean cross-section. This is a consistent result with all the null results, but this is anyway impressed or important progress for final conclusion, because with the independent sodium iodide crystal, we start to give constraint on gamma's interpretation. But still, we need the model independent check that we should do the annual modulation analysis that are basically ongoing in both Anice and the cosine experiment. One issues are background level. Gamma has about 1, but this background is 3 to 4 times higher than gamma. That maybe, we have a hard time to clean up the gamma, even with a large amount of data. So then 3 independent groups are growing or making ultra low background sodium iodide crystals. So cosine and picoron and Saburo succeed to grow crystal. This is, I think, a pretty good progress. So in my thought, around 2020, we may have a phase 2 experiment, at least one of them. Then a 3-year operation will clean up the gamma. In this case, we should use the crystal better than gamma. Okay, so just before conclusion, the updated status is here. All these 3 best limits are already replaced from the PDG 2018. So this is really moving fast. So gamma Libra are not appear in this parameter space, but they are not rejected yet. Okay, so let me conclude. Search for high mass region are dominated by liquid genome, and they are incredibly fast progress. And various techniques are developed for low mass dark matter. They are quite comparative regions. And next generation experiment in both low mass and high mass are well on the way. And gamma Libra signal is now 13 sigma, is incredible. And the independent verification are critical importance, and a lot of efforts are ongoing. I would say our field are quite active and healthy with the well-established next generation experiment, and also supporting frontier technology development. And in that point of view, discovery can be in this field can be made anytime and any place. Thank you very much.
Questions for Dr. Lee? You have to wave your hand. It's hard for me to see. Okay, I can't see anyone. Am I missing anyone over there? No, okay, I've got a question actually. So we're rapidly approaching the neutrino floor. Should we be afraid or should we be excited about that?
Should be excited, I think. But in my understanding, spectral shape might be different with the typical WIMP in LG or xenon enton, so we can partially discriminate the neutrino, and then maybe we can do the neutrino observatory you can be.
Okay, thank you. Let's thank the speaker again. Next up, we have a topic very dear to my heart. Dr. Yanis Martsnias will be talking about axion searches.
Great, 안녕하세요. I'm the director of the Center for Axion and Precision Physics Research, an IBS center, and we are located at KAIST. And for those who ask, Korea is an amazing place. If you get a job, get it. So this, I'll claim over here that this decade belongs to axion dark matter experiments. And the question to answer in this talk is, are axions a significant part of the local dark matter? Actually, this is what we'll try to answer. Strong CP problem, axion parameters, and dark matter. The QCD Lagrangian contains a theta term violating both parity and time reversal symmetries. And we can test this. We can test it by looking at the neutron electric dipole moment. And you can look at the reduced mass of the neutron over here, lambda QCD. This is dimensional analysis. This is the type of electric dipole moment you expect. If you do it correctly, this is what you get. And indeed, the electric dipole moment experimental limit, not a measurement, it's 10 to the minus 26 electron centimeters, meaning that theta bar QCD is less than 10 to the minus 10. This is supposed to be of order 1. And in simple terms, the strong CP problem is really the experiment show that it is at least, theta QCD is at least 9 to 10 orders of magnitude less. And the question is why? Pechey and Quinn said this theta term is actually compensated by a dynamical field, and it goes to 0 naturally. And Wilczek and Weinberg said, not too fast, you get an axion if you get into that. They assumed this would be a heavier particle, and that was excluded very quickly by the experimentalists. And then Professor Ginny Kim said, he put together a hadronic axion model, which means an invisible axion, as he called it, and he also suggested it could be the dark matter. Light cousins of neutral pions, the mass is really light, the coupling is very light. This Mexican hat is tilted, that's how you get the mass, the oscillation, 6 micro eV for a scale of 10 to the 12. The parameter range, the heavy ones, so this is the correlation between FA and the mass, the axion mass. The heavy ones are excluded by experiments and then by the life of the stars. And over here, you get a region which is just right to have the correct dark matter parameters. And you see here, it goes from a few milli-eV all the way up to micro-eV. But this limit you can bypass by having, if the Pechey-Quinn symmetry is broken down before the inflation, and that would be this case. So in essence, the whole thing is open. I want you to look at this, and I have a couple of comments about this. First of all, this is a log-log plot, which means we are in trouble. The range is too large. And this is the axion coupling to 2 photons versus the axion mass. The second thing to look at is this band really defines the axion. So axions here solve the strong CP problem. And anywhere else doesn't. But the most important thing from this plot is there is a goal, there is a target, and there is a floor. That is, if we reach all the way down over here to the 10%, let's say, of the axion dark matter, of the axions being 10% of the dark matter, then we would have answered the question whether axions are part of the dark matter question. So we know where to go. Even though it's very, very hard to go there, we will try. Some numbers, the dark matter, 0.3 to 0.5 GeV per cubic centimeter. For these kind of axions, the system is classical, the lifetime very long, cold dark matter, kinetic energy. You get the axions to oscillate in a very, very narrow frequency. So 10 to the minus 6, a quality factor of 10 to the 6. This is the velocity range. This is the RMS bound in galaxies. And the mass range, it has to be larger than 10 to the minus 22 EV. That's the size of the galaxies. And coherence length, the de Broglie wavelength, it's 1 meter, and then for 1 millieV divided by the mass. So below that, as we said, we are going to target something below that mass, below 1 millieV. The de Broglie wavelength, that is the coherence length of the axion field, is going to be big enough for a macroscopic detector. The axion couplings, how do you couple to things? The gauge fields, electromagnetic fields, the gluon fields. The electromagnetic fields, these are supposed to be vectors. The point there is if you apply a magnetic field, this is the oscillating axion field, you will get a mixing of the axion with the electric field, a mixing. So you get a wave that is always propagates together. Here, the gluon fields, the coupling to gluon fields, you can get an oscillating electric dipole moment, for example. And this is also being used, and I'll talk about this. And finally, coupling with axion field gradient. If you have the field, the axion field, the gradient looks like a pseudomagnetic field. And we are also using that coupled with spins. A lot of activities are going on. I didn't put everybody on the map. I wanted to emphasize that DESI is coming up very fast. It's just taking off on these axions with a lot of activities, really impressive. But also we have the University of Western Australia. They got an excellence grant to go after dark matter, and axion is a big thing there too. We are here, obviously, and CAST and Florida, Eastern and Western, the US. The activities are large. These are kind of meetings you used to have 40, 50 people even 10 years ago, and now we can't even get a talk. It's just too busy. And we just had a DESI in Hamburg, more than 150 registered participants. Major activities, ADMX, that's the leader, Haystack, IBS, us, and then organ, high frequency. These are all cavity stuff. Then we have Cloy magnet, Frascati. They are in the works. They are trying a large Cloy magnet to use it for lower frequencies. MatMax, this is very impressive how it's developing. ALPS, ADESI, coupled Fabry-Perot resonators. CAST-CAP, actually, we have just installed 2 cavities there to use rectangular cavities and TE modes. I'm not going to say any more on this. Abracadabra, MIT, toroidal magnets, and dark matter radio. If you have a large magnet, they are looking for a collaborator, so it's opportunity. And now these are all cavity dark matter experiments. These are Casper electric, these coupling with spins, Casper axion wind, oscillating neutron electric dipole moment, and something that's going on now, JEDI at Jülich axion electric dipole moment using a storage ring. And finally, GNOME, axion domain walls, or axion stars. You wouldn't know you've been hit by an axion star, but we will be able to sense it maybe by sensitive magnetometers. This is an international network, different places around the world. It's cheap to install, but it's very powerful once you have correlated signals. And then Ariadne axion-mediated long-range forces and no dark matter needed. I'm not going to talk about these things. Here, there is a good overview on the axion field. This is a must-read document. Light shining through the wall, and you see all sorts of parameter polarization, spin-dependent, helioscopes, and so on. Haloscopes, pickup coil, dish antenna, dark matter-induced EDM, spin precession in cavities for electrons, and atomic transitions, and so on. A lot of activities going on right now. The figure of merit, everybody's using magnetic fields, almost everybody, but in different ways. Vacuum birefringence, this is B square L, that's the length of the magnetic field. Light shining through the wall, B fourth L to the fourth power. Helioscope, looking at the sun. It's B square L square A, or you can rewrite it as B square V, but also the length is important. And then haloscope, this is the dark matter halos. Haloscope experiments, B square V. The energy content of the magnet, as big as possible, is important, and then you want to be able to do high frequency. And this is Casper and quarks and so on. Measure nothing but frequency. Okay, this is how the axion does, but you can't see it. It's oscillating at one frequency. And then what you do is you put a DC magnetic field, it mixes the axion field with the electric field. And that is the fundamental principle of how you get to detect an axion detector. All right, you have the microwave cavity, a magnetic field, and then you use a resonator to build up the electric field. And the spectrum would look like this. This is the power versus frequency, and then this is the cavity width, and on top of this you get a little thing, and that's supposed to be the axion. How much power? You get power out of vacuum, which is very little, 10 to the minus 22, but still it's out of the vacuum. All right, the axion to photon conversion power is indeed very small, and that's why you have to do a lot, and you don't know the frequency, so you have to do a lot to do that. Look at this, the parameters to look for, because you don't know the frequency, DFDT, you look, the magnetic field is important, the volume is important, the temperature of the whole system, by that we mean the physical temperature plus the noise, electronic noise of the detector, and then the quality factor of the resonator, whatever you have. And this is an ADMX study. This is a study of the power versus the integration time. And this is how much they could go down to 1 RF photon per minute. That's 1/100th of yoctowatt. It's 10 to the minus 26 watts. This was done on the bench. All right? So if we knew what the frequency is, we would all be able to have an axion dark matter experiment. It's like looking in a phone book, and the way to look for it, the way we look for it is we have a simple experiment looking at for each frequency. It's very cumbersome. All right, once it's discovered, anyone will be able to dial in and talk to it. Every institution will have this axion dark matter experiment. The first one was done at Brookhaven by the RBF collaboration, and you can see it still resembles the new systems. This is what we had. And the questions often asked back then, it was, the dark matter exist? Is dark matter really there? And axions, do axions exist? These questions are less asked now. All right, this is what we did. At that time, let me go. This is the RBF. This is the University of Florida, you see. And then the ADMX came along in mid-90s. That's the group in 2012. now not much larger, but there are a lot more institutions going on, a lot more expertise, and they have the detectors is the key over there, and the cryo. Two things happened. Dilution refrigerators became possible to do. Dilution refrigerators, the technology just grew amazingly well, and large volume, they went to lower frequencies. The low noise amplifiers from 12K we used at the time, we went down to 1K, and now we are also going down below 1K. All right, this is ADMX. If you see over here, there is a little line, and if we focus in, this is what we see. This is published, and Gray Ripcat said, we didn't find an axion over this narrow range. Most importantly, we could have. This is the first exploration to the plausible DFSZ coupling in the prime mass range for dark matter discovery could come at any time. And it is a correct statement. That's us, IBS-CAPP, and this was, by the way, January 2017, and if you go there, it's a very busy place. You don't have space anymore. We have a lot of refrigerators, powerful ones, and a lot of magnets. These magnets are coming, and this is our plan. We'll put it all together, and funding limited for our big magnets, the workhorses, and that's what we expect to do with a single cavity. And after we finish that, we will be possible to go beyond 10 gigahertz. That's other experiments. Now, let me rush you through a few more slides. This comparing the different type of experiments over here, but Grenoble is getting into the game with a large volume, large field magnets, and that is in an impressive way, as a matter of fact. Telescopes using spins. The NMR, what you do is you align the spins, the nuclear spins, with a DC external magnetic field, and then you can precess, you can use an oscillatory magnetic field to precess the spins. On resonance, you're going to get the spin precession, all right? And this spin precession okay, let me wrap it up. This is what Casper now and Axion and Phase 3 can do, really impressive. These solar axions, X-rays, this is that, with different experiments, CAST, YAXO, and YAXO Plus, ALPS. I guess I underestimated the time, and reverse B field direction. This is a MATMAX. This is a very impressive experiment. 30 seconds on that. The axion and the electric field are mixing. At the interface, you can get a bouncing, the photon. The axion does go through, but the photon bounces, and they want to utilize that. Look at the magnet, 10 Tesla magnet, and 1 meter in diameter, 2 meter long. All right, this is how it looks. It's going to look. It doesn't look like that right now. The abracadabra dark matter radio over here, the clash, action in YAXO, ADMX, CAPP, MATMAX, and so on. And in this range, it didn't take long for someone to come up with an optical photonic crystal to cover even that. And let me finish now that the axion dark matter efforts are becoming really very exciting. A discovery can be announced at any moment depending on the frequency. You just need the frequency to know what, to hit it right. And within the next 5 to 10 years, we may very well know whether axions are 100% of the dark matter. Thank you very much.
Thank you, Giannis. We have time for one question. Just step up to the mic if you would. Is it someone's moving to the mic? No, okay. So Giannis, can you predict how long until we find the axion?
It depends on the frequency. If it is between 1 to 10 gigahertz, in the next 3 to 5 years, we'll find it for sure. If it is above that, it's going to take 10 years. And if it is below that, it's going to take 10 years, the same 10 years. So the next 10 years is going to be interesting. It has to be there, and it has to be 100% of the dark matter. So.
Okay, well, thank you again, Giannis. So next up, we have Manuel Dries, who will tell us about dark matter theory.
Let me start by thanking the organizers for inviting me here. In fact, for me, this is a very special place because 17 years, 6 months, 9 days, and a few hours ago, I got married right here at COAX. But okay, now back to business. I am supposed to talk about dark matter theory. Now, the last 25 years or so, I've been mostly working on astroparticle physics. And astroparticle physicists have to deal with two standard models. There's the standard model of particle physics that every particle physicist knows, but there's also a standard model of cosmology, which came into existence maybe 10, 15 years ago. Dark matter is very much part of the second standard model, but not of the first one. So let me spend a few minutes of walking you through the evidence why we are pretty sure that dark matter, in fact, does exist and is part of the standard cosmological standard model, and also why it is not something else that can explain this cosmological or astrophysical evidence. Modified gravity is sometimes bandied about, or primordial black holes, but these don't really work. So that leaves us with particle physics candidates. There I will first give you an overview of what we know about what properties that particle dark matter has to satisfy, and that's actually not very much. And then I will specify or concentrate on one particular class of candidates that are so-called weakly interacting massive particles, because that's what I'm working on before summarizing. So evidence for dark matter actually comes from a large variety of scales. When we first define dark matter for you, that's matter, which means something which gravitates, but it should be dark, means it should neither emit or absorb light. Actually, it's really transparent rather than dark in the colloquial sense. Now, the first evidence, or on the smallest scales, still kiloparsec or so, comes from the measurement of rotation curves. This refers to spiral galaxies which have an about rotation, and you can measure the rotation velocity as a function of the distance. Once you are outside of most of the mass, or most of the visible mass of the galaxy, then you expect that the rotational velocity should scale like 1 over square root r. That's, for example, true for the rotational velocity of the planets in our solar system, because almost all the mass in the solar system is in the sun. However, most observed rotational curves do not behave like that, and from that we can conclude that most of the galactic mass is not in the visible stuff, it's not in baryons. So usually people show at this point the rotation curve of a distant galaxy. I'm instead showing the rotation curve of our very own galaxy, which is actually a lot harder to measure than that of distant galaxies, but it shows the same basic behavior. We are approximately here, by the way, and you see that here from us outward for another factor of 10 or so in length at least, the rotation curve is basically flat. And we are already outside most of the shining baryonic mass of our galaxy. So that flatness here you cannot explain with what you see in stars and gas and so on in our galaxy. So that was galaxies. The biggest gravitationally bound structures in the universe are clusters of galaxies. Here is the Coma cluster. So just a bunch of galaxies which are gravitationally bound together. And in clusters of galaxies, you can actually measure or determine the total mass of the cluster in at least 3 different ways. The oldest way is the one pioneered by Fritz Zwicky more than 80 years ago that just uses the virial theorem, which tells you that the average kinetic energy should be related proportional to the average potential energy in a bound system, and that is, of course, proportional to the mass, because that's what does the binding. That argument works for galaxies. The same argument also works for single ions. That, in fact, tells you then that the temperature of the hot gas, which is in the center of a cluster, should also scale like the mass of the cluster. In fact, this gas is so hot that it primarily emits in the soft X-ray wavelength band, which is why, and those you can only observe from space. So for Zwicky, this hot gas, which actually makes something like 80% of the baryons of the cluster, was in fact dark. For us, it's not anymore. Finally, and most directly, you can use gravitational lensing if you find some background sources behind your cluster to measure the mass of the cluster. And the results of all these determinations are consistent. They tell you that something like 80% of the mass of the cluster is not baryonic. It's not what you see in baryons. Now, turning to the larger scales, cosmology, the most famous cosmological observation by now is probably this cosmic microwave background, where when you plot the power spectrum, as it's called, you find this beautiful curve here. And this is 2,499 measurements, actually. Not all measurement is represented by a data point here, which is fitted by 6 parameters. So it's very, very impressive agreement. And in particular, this pattern of wiggles comes about because you have 2 different kinds of matter there. You have baryonic matter, which is ionized up until the point of recombination, so it feels a strong pressure, and something which has a pressure can build acoustic waves, can form in there. The acoustic waves are responsible for these wiggles. However, the detailed pattern of the acoustic waves is also affected by the presence of a second matter component, which has no pressure. So you need both of these matter components to explain detailed pattern of this maxima and minima. And from that, you actually get both matter components very accurately. There are additional cosmological arguments supporting this. The density of baryonic matter you also get completely independently from analysis of Big Bang nucleosynthesis. This is not quite as accurate as a CMB analysis, but completely consistent. Finally, there is another fairly simple argument from structure formation that also relies on the CMB, not so much on the detailed pattern, but just on the overall size of the density of the temperature fluctuations, which is very small. And starting from so very small perturbations, without dark matter, it will take rather a long time to form galaxies. However, we have seen galaxies, very, very old galaxies, and that, I believe, is the current record holder over there. It doesn't look like much, but it is, in fact, a galaxy at a redshift of 11. And at this point, the universe was just a few 100 million years after a Big Bang. And you can't possibly make a galaxy with a few 100 million years after Big Bang without dark matter starting to clump before the baryonic matter can. That's another very strong argument for dark matter. So let me summarize, and we have many independent observations at distance scales between kiloparsec or a few kiloparsec all the way up to the Hubble scale, gigaparsec, which can be explained consistently if and only if cold dark matter exists. So that's the status. But then, all these arguments rely on standard gravity, meaning on GR, or in fact, in most cases, just Newtonian gravity will do. What if this is incorrect? What if gravity is particularly stronger at weak accelerations? That's the idea behind MOND, the modified Newtonian dynamics, as espoused by Milgrom and collaborators. Well, you mess around with GR at your peril, I would say. GR has by now passed a large number of very, very accurate tests, some of them quite recent. For example, the analysis of binary pulsars, where people in Bonn, my home place, play a big role. And of course, as everybody knows, also the observation of gravitational waves also agree very well with predictions of standard GR. On the other hand, it's a very difficult, in fact, this MOND is just a very phonological description. It's very difficult to formulate a consistent classical field theory out of that. Particularly this Teves attempt appears to be basically excluded by this binary pulsar analysis. Finally, even if you have MOND, there are some observations would still require dark matter. The most obvious of them is this famous bullet cluster. So therefore, this MOND stuff looks very, very implausible to me. So let me briefly show you the bullet cluster. This is actually a superposition of 3 different images. There are these galaxies here and there. Then in red, you see an X-ray image, which is the hot gas. Once again, hot gas is bulk of baryons in a cluster. And you see that this hot gas when this right cluster here, which is actually the bullet, went through the bigger one, got shocked and got slowed down relative to where the galaxies are. Finally, in blue are contours of constant mass density as inferred from lensing studies. And you see that most of the mass follows, most of the mass density inferred from the lensing follows the galaxies. However, most of the baryons are here. So that tells you that most of the mass is not where most of the baryons are. And there's no way you can fake this with some MOND kind thing. You really need something else beyond baryons to be over here. So MOND will not do it. What about then primordial black holes? Maybe that's something that could explain dark matter without having to put any new particles. In fact, there are some arguments in favor of the existence of dark matter. This first observed binary black hole mergers by LIGO, they had masses which were maybe a little bit large for astrophysicists for modeling stellar mass black holes, although I'm not sure whether this is really alarming. And also sometimes the argument is used that is made that it's a bit difficult to understand the presence of very large, like mega sun mass black holes in AGNs already at large redshift. Maybe you could see them also with primordial black holes. However, there are also a bunch of counter-arguments. First of all, it's very difficult, in fact, almost impossible by now to find a mass range where these black holes can make a large fraction of dark matter. Also, in order to make primordial black holes, primordial means they have to form in the first 1 second of the universe before BBN, otherwise they would be counted in the BBN baryon counting, and they are not there. And to do that, you need density perturbations at very small scales, which are at least 10 million times larger than the density perturbations that we see in the CMB. Now, you might have heard that there is a power index, in fact, in the CMB, so their density perturbations are not entirely scale invariant, but this power index, in fact, is less than 1, and it goes in the wrong direction. Finally, even if you engineer your power spectrum to make black holes at some desired mass range, and you have to make it cut off very fast again, since otherwise it will overproduce black holes at a slightly smaller mass range. So that would need some severe fine-tuning to work. So this also looks very, very implausible to me. Here's a recent compilation of various bounds on the total abundance of black hole, where you would have to go to 0 here in this quantity if you wanted to saturate the total known dark matter mass in black holes. And this is various microlensing and femtolensing searches here. And over here is this bound from not seeing the evaporation of by Hawking radiation of black holes. So black holes also don't seem to be the answer. So we do need particles to explain dark matter. And that argument is completely independent of what LHC sees or doesn't see, or what LZ sees or doesn't see, or any particle physics arguments, really. So what do we know about these particles? Well, the mass range is, in fact, quite large. The lower bound, as we heard in the previous talk, for bosons is something like 10 to the minus 22 eVolt. It is an inverse galaxy radius. Upper bound for it to be called a particle would be M-Planck. That's roughly 50 orders of magnitude we have to look for. For fermions, you only have 25 orders of magnitude, roughly, because Fermions can't condense, so they have a finite kinetic energy always. And for that not to be too large, they have to have a mass of a keV or so at least. That same bound applies if you produce your bosons thermally. Then, of course, we know that the lifetime ought to be larger than the age of the universe, obviously, otherwise the dark matter would be gone. In fact, for dark matter masses above a GeV or a few GeV, the bound is considerably stronger. It's more like 10 to the 25 or 10 to the 26 seconds, because otherwise we would have seen the decay products. Finally, from the bullet cluster, we know that the self-interactions cannot be very large, but very large is really not a strong constraint. And we also know that dark matter should be significantly less dissipative than ordinary matter, because we need the visible part of galaxies to be embedded in dark halos which do not collapse. But for that, you have to realize that ordinary matter is dissipative, first because we have a massless photon, but second also because we have a very light electron, which is much lighter than the proton. Almost all the dissipation comes by emission of the electrons, not the protons. So if you avoid one or the other, you're basically okay with your dark matter model. So that's basically all we know. Now, you also know the overall density of dark matter. That's one number that one theorists have to reproduce when they're constructing dark matter models. Now, you may say that this is not very much we know. That's true, but nevertheless, it is enough to exclude every single particle from the standard model as a candidate. Therefore, this is really very compelling evidence that there is something beyond the standard model. And once again, this is independent of what we find or don't find at the LHC or any other particle physics experiment. So, of course, there's a large list of candidates that people have cooked up, starting with very small masses, fuzzy dark matter, axions, sterile neutrinos, dark photons, of massive vector bosons, basically, gravitinos, WIMPs, WIMPzillas, and a bunch of other candidates, which I didn't bother to write down. My own preference would be a dark matter particle which does something other than just dark matter, which has another independent reason for existing. And that's, of course, very much true for the QCD axion. For some WIMPs, in particular supersymmetric WIMPs, but also, for example, the gravitino. In addition, it would be nice, of course, if you could actually detect this thing using vaguely particle physics methods, which is again true for the QCD axion, as we just heard, and again also true for at least some of the WIMPs. Now, I personally never worked on axions, so for the rest, a few minutes of my talk, I will spend talking about WIMPs, obviously. So the nice thing about WIMPs is that from this simple calculation and assuming standard cosmology, you get the right thermal relic density if you have an annihilation cross-section which is sort of picobarnish, so like a weak scale cross-section, hence the name weak. Weakly interacting massive particles really means something which is, at least the cross-section of which seems related to the weak scale. And that's quite a funny coincidence at the very least, because in the constants of proportionality that I haven't written here, there's things like the Planck mass appearing at the temperature of the cosmic microwave background and so on. So it's not at all obvious that this scale should pop up there. Now you can search for WIMPs in various ways, as we have heard. Unfortunately, none of them have really yielded much of a signal yet. Neither the indirect searches nor the collider searches. In fact, at colliders, you usually can't really search for WIMPs themselves. What you can look for are mediators which mediate the interaction of the WIMP with standard model particles or partner particles like squarks if your WIMP happens to be supersymmetric, or changinos, that you heard earlier today. And of course, there are the direct searches, which also haven't found anything yet, except that Dharma still claims to have a signal, as we also heard just a few minutes ago. So here is the most recent direct search result, which we also saw a few minutes ago. Let me just point out here that in the large mass range, the actual bound is slightly weaker than the sensitivity, projected sensitivity. Of course, I shouldn't make too much out of that. So let me briefly explain to you the shape of this curve, and that explains then also much of the recent model building activity. So the kinematics, in fact, determines much of this. This is really physics 101 stuff, non-relativistic elastic scattering, which tells you that if the WIMP is much heavier than the nucleus, the energy of the nucleus becomes independent of the mass of the WIMP. The kinematics sort of saturates. In the opposite limit, the maximal energy of the nucleus scales like WIMP mass squared divided by nucleus mass, so it becomes very small. So for small MK, the recoil energy just becomes smaller than your threshold, and you completely lose sensitivity, as shown here. So there, the bound just completely evaporates. On the other hand, for large MK, the kinematics saturates, which means that the flux just scales like 1 over the mass of the WIMP, because what we know is the mass density of the dark matter, but of course the rate depends on the number density. And therefore the bound of the cross-sections, that's a typo here, should scale proportional to MK, not 1 over MK. So that means we have, for theorists trying to evade these bounds, you can do in 3 directions. You can look at very light WIMPs, so that your threshold, you go below the threshold. That gives various opportunities for small, relatively small energy experiments, be it colliders or even fixed target experiments. For direct detection, as we heard, you need new technologies to explore this domain. It's not so clear where the WIMP region really ends. Very heavy WIMPs go to the other end. How heavy can it be? Well, there's an old argument that says it should be a mass below about 100 TeV. More recently, people have been actually constructing models to try to push to the large mass. And with co-annihilation, for example, with a Beano with stop, you can go up to 6 TeV. And then we go to the punchline for this particular resonance model, which is that you can have WIMPs with up to 26 TeV even. So that would be, so in this case, the mediator would be twice that mass. So it would be a Z prime at 52 TeV, which would be comfortably beyond the reach not only of the LHC, but even of a putative 100 TeV collider, EP. Finally, you can also try to go below, so make the cross-section smaller. In standard cosmology, this tends to give you too many dark matter particles. Remember that the relic density was inversely proportional to the cross-section. So there, people have been looking at ways to get around that by slightly modifying the cosmology. And here, one can make use of so-called moduli or Poloni fields, which are generic, exist generically in supergravity or string theories. These are massive fields which couple only gravitationally. So they live very long because their coupling is so weak. And because they live so long and are matter, they may then dominate the universe sometime between inflation and now. And with that, it opens many additional possibilities. Let me hurry up a little bit here to keep in time. You can either increase or reduce the WIMP density in this way. You can reduce it because when you calculate the WIMP density, you always normalize to the entropy density. And the case of these moduli fields, they produce entropy. If they don't produce also WIMPs at the same time, that will reduce then the predicted WIMP density. And of course, they can also increase the WIMP density, for example, by direct decays of the moduli into your WIMPs. So most importantly, for evading this type of production constraints is the going down in cross-section. But it turns out that if you want to use this mechanism to make WIMPs with small cross-section compatible with standard cosmology, you need to have, first of all, this decay branching ratio of the moduli into the WIMPs to be less than 10 to minus 4 or so for 100 GeV WIMP. And also, the moduli should not be too heavy, because otherwise you get back into standard cosmology because they decay early. Okay, so let me skip the rest of this and just go through my summary, the take-home messages. I hope I convinced you that dark matter does, in fact, exist. And it almost certainly consists of some new kind or kinds of particles. It's not part of the standard model. It's really very solid evidence that standard model of particle physics is not complete. We don't know much about these particles. other than that they exist and have some mass. Most likely it has not been found yet, although every few weeks somebody will claim that dark matter has been found or evidence for dark matter in some cosmic ray observations or whatever. I don't believe any of that. And the oldest and simplest candidates for dark matter, like axions, some WIMPs, gravitinos, they are still very much not excluded. Although in case of WIMPs, at least one can say that the parameter space is getting squeezed by this amazing progress in direct searches in particular. So theorists are spending some ingenuity to construct models that can evade these bounds. Thank you.
Questions, please.
You brought up the bullet galaxy as evidence for dark matter.
Cluster.
And there was an analysis reported some years ago by Lee and Komatsu that found to explain the bullet galaxy with dark matter, you needed an implausibly large collision velocity. Would you comment on that?
I think the collision velocity can be determined from the the heat of the shock wave. It has nothing to do with dark matter as far as I can tell.
Are you aware of this paper by Lee and Komatsu?
Not really, no.
You should read it.
Thank you. Do we have another question? We have time for another question. Please step to the mic.
You mentioned these upper limits of 27 TeV, 100 TeV. Can you just comment where they come from and how solid are they?
This 100 TeV is just unitarity. If you have elementary particles, the annihilation cross-section is bounded by unitarity. And because the relic density goes like 1 over cross-section, if you have an upper bound on the cross-section, which goes like 1 over mass squared, basically, that gives you then an upper bound on the mass of the WIMP. This 26 TeV is in a particular realization, which is a weakly coupled resonance. There you can go up to a 26 TeV, which is already, for the next few decades anyway, close to infinite anyhow.
Okay, one more quick question.
You have so many different cosmological observations, and on the other hand, you have so large mass range. Is there none of the observations favoring one over the other?
No.
No, okay.
Okay, well, we better move on. Let's thank Manuel again. Okay, we have next Masashi Hazumi speaking about CMB, cosmology, and other astroparticle physics.
Okay, great. Thank you. 12 years ago at ICHEP 2006 in Moscow, I gave a plenary talk on new results from Bell and Babar. And since then, I jumped into the measurements of cosmic microwave background, CMB. So today, I'm very happy to be here at ICHEP for the first time in 12 years. So the title given to me is CMB, Cosmology, Other Astroparticle Physics. Sounds like a mission impossible. So to share my difficulty, I made this. You know, suppose you live in this parallel world, and then you're asked to give a talk on Higgs flavor physics and other particle physics. Say, well, what are you gonna say? So, well, you should say I feel honored, but then you should think about what the scope is. So I really need to be selective, and then what I do is to really select beyond the standard model related topics. So after giving some introduction, I'm gonna go to CMBB mode for testing inflation and quantum theory of gravity and dark energy and some other beyond the standard model related topics, including neutrinos in cosmology. Okay, introduction. So while I'm talking, I just show this very nice movie made by ESA to explain how this CMB power spectra are made, calculated. So the first thing I should say is modern cosmology is a precision science like high energy physics. In particular, the CMB is really a nice tool for us. So why are CMB measurements so precise and accurate? I have 4 things to say here. First 2 are related to CMB nature itself. First of all, we have a linear evolution from initial state to CMB emission, so there is no nonlinear uncertainty. And then after the emission of CMB, it was well preserved until today. And the latter 2 are related to the observations. Actually, since we are taking correlation between 2 points in the sky, the precision you get, this power spectra, are inversely proportional to observing time, more or less. So whereas most of the particle physics experiments are having this square root of time t. And we also have a remarkable development of observational instruments, so that's another reason. Okay, and of course, other probes, such as 3D galaxy maps, are also very useful and complementary and or unique with careful treatments of biases and other nonlinear effects. And one thing I should say is that today I'm not gonna talk about new Planck results, but I know that the Planck legacy release will come soon in a week, so stay tuned. Just to be clear about what I'm talking about, and in particular about the expansion of our universe, just a little bit too pedagogical maybe, but let me show this cartoon. First, you see these galaxies are, are going away from each other. And you put here this sort of dices to show explicitly that you have a space. So then what I show now is a wrong description of the expansion, which is this. Space stays the same, but it's just galaxies are going away from each other. That's wrong. What we are really having is the space itself is expanding, and galaxies are just sort of markers. So in a sense, galaxy stays in the same place. And so that's the essence of the cosmological expansion. So precision measurements support a remarkably simple picture today, which is called the lambda CDM, which is a standard cosmology, based on the general relativity, Einstein's equation, plus cosmological principle. And because of that high symmetry, now you have just one parameter scale factor A, which corresponds to this, the size of the side of the cube, which you saw. And of course, now I'm assuming the flat universe. But then you come to this Friedmann equation for time evolution of flat universe. And once you have this equation, just like any other physics problem, you need the initial condition to solve this. So here we assume the initial adiabatic Gaussian perturbation, which is consistent with the inflation hypothesis. Then only 6 fit parameters are sufficient to describe the current set of precision data. So flat universe assumption works fine. Here are, so the choice of 6 parameters is not unique, but here's one example from Planck's 2015, 6-parameter fit to flat lambda CMDM cosmology. And other parameters are derived. Examples include dark energy density and the life of the universe, age of the universe. So the first 2, baryon density and cold matter density, precisely determined. And from that, you know that just a 5% baryon and 26% dark matter and 69% dark energy. And next to this one is related to the size of the universe. And the fourth one is a reionization optical depth, which is something to do with the late evolution And last two, scalar spectral index and power, the coverage of perturbation are for initial conditions. So then you need to, you now start thinking about the extension. So far, there's no evidence for need to introduce an additional parameter. But this may change with more precise measurements in the future. This lambda CDM is not the dogma, just the current understanding. In particular, following are interesting. One is this tensor to scalar ratio, which I'm going to talk about from inflation. And another is the dark energy equation of state parameters. So, but the idea here is really we have a commonality shared with high energy physics. You want simple theory, and you want to stick with that, really. So, for instance, if you take this R as an example, this is really a prediction of inflation. You really want to introduce this. It's a minimal setup, more or less. So here's to explain what I'm talking about. Here's an iron in my hotel room. It's a simple one. You prefer that rather than some complicated ion system that I found on the web page. So this one is not good. So once you find this, your favorite tool, what you want to do, what you should do is to use this tool in extreme environments to see what happens. That's really what we're doing. And I really think this is here's a little bit of difference between cosmology and actually astronomy. Astronomy sometimes sort of enjoys the diversity, which is one way to go. But this cosmology really shares this same spirit that the high energy physics people have. So you really want to test this in extreme environments, just like this. So this is what you should do, okay? So let me move on to CMB mode for testing inflation and the quantum theory of gravity. Okay. So physics of cosmic inflation. Inflation is a primordial accelerating expansion. It successfully solves problems of naive Big Bang model, which is great. But underlying physics is unknown. We have a leading hypothesis to introduce a new scalar field phi called inflaton with some potential. And this serves as a source of acceleration of the universe. With a known matter and radiation, you cannot create this accelerating universe, whereas inflation is really a primordial acceleration. In case of single field slow roll inflation, which means that you just introduce a simple one field, which everybody likes, right? Simplicity as guideline, you come to this very intriguing, interesting equation about the relation between the potential and R, which is a tensor to scalar ratio, one of the cosmology parameters that I mentioned. So this R is really a key parameter. If you can establish non-zero R, you have a chance to really quantify the potential height. And as you can see here, somehow, for some reason, we don't know, this is pointing to the gut energy. How do we measure that? That's the next question. And the CMB mode signal of inflation, that's the answer. Because inflation predicts the primordial gravitational wave emission. This remains in a later universe. When the CMB was emitted, that CMB was affected by this primordial gravitational waves. As a result, if you look at the curl map, the polarization map of the CMB, you should find this curl pattern as a fingerprints of inflation, which is called the B mode. And to date, the CMB mode is the best probe for the primordial gravitational waves. And in a sense, sometimes people call it indirect or direct. To me, this is sort of a direct detection. But your experimental apparatus is actually CMB, which was put long time ago. And the measurement was done already. We're just taking out that information right now. So that's the view I have. And here's just a comparison between CMBB mode sensitivity versus interferometer sensitivity. You see that we already have this sensitivity from Planck and BICEP, which is already done, whereas future interferometer experiments are much less sensitivity. So this means that if we successfully discover CMBB mode, primordial one, that will provide a clear target for future space interferometer, no matter how hard it is. So because of that, here's an excerpt from the final report of the task force on cosmic microwave background research more than 10 years ago. This is called the WISE committee report, so chaired by WISE. It says detecting primordial gravitational waves would be one of the most significant scientific discoveries of all time. And for WISE, it makes sense for WISE to say that because, of course, LIGO discovery was great, but here's a big leap from LIGO to CMBB mode because LIGO's gravitational waves are with classical origin, whereas this CMBB mode gravitational waves have the quantum origin, the space, quantum fluctuation of space itself was the origin, should be the origin. So, and this was really a kind of a dream like 20, 30 years ago. Now it's a reality, becoming a reality, this measurement, thanks to the development of the modern CMB instrument. Here's an example, polar bear, which I'm working on. The telescope is in Atacama, Chile. The total dish size is around 4 meters. And this is just a one-night observation. You just choose one patch of the sky and just try to follow this with the so-called constant elevation scheme. And we use a TES Bolander array made by the UC Berkeley group, and then see this sort of polarization map. So 4 years ago, we had lots of upper limit measurements, but then finally, for the first time, polar bear touched on the B mode. But note that you see here are two structures. This one is actually the primordial B mode prediction. This one, which is another one, a secondary effect made due to the gravitational lensing. Even if you don't have any B mode, primordial B mode, during the course of the cosmic evolution, you have gravitational potentials. So you are viewing the polarization map of CMB through the distorted lenses. So inevitably, you have created some curve patterns. But the nice thing is that the scale is rather different. So this multiple moment, larger multiple moment corresponds to the smaller scale, smaller angular scale. So this secondary effect called the lensing B mode is concentrating on the high L or smaller scale. So you can distinguish between two. But nevertheless, this was a demonstration March 7th. And a week after that, we had heard about this big announcement from BICEP 2. We were so shocked. And then, but immediately after this claim, there are several sort of arguments and claims that this was just based on one frequency measurement, so the foreground removal is worrisome. And then they went through the joint analysis with Planck, where Planck had 350 gigahertz for dust cleaning up. So then it went down. So it disappeared. And during the course of that, we also had this other measurements from SPT pole at the South Pole and ACT pole in Chile, Atacama. So this is the situation. And then this is 2015, and then 16, there's some update. And then last year, we also made some update. So that's the situation. And then, but this is already really great in terms of quantum gravity testing and the inflation testing, because here's the current situation, summary of the current situation. The vertical axis is the tensor to scalar ratio R, whereas the horizontal axis is one of the lambda CDM parameters, scalar tilt. Then you have a very nice constraint here. So first of all, although I didn't explain fully, this scalar tilt is now firmly less than 1, 0.968, which is consistent with the prediction of the inflation. Inflation predicts that this is a little bit less than 1. And another thing is simplest chaotic inflation model is already ruled out. So this is amazing to me. So the simplest model is really ruled out. And the limit on R at the moment is 0.07 at 95% confidence level. So the main game is that we want to really reduce this, the error on R. So here is a list of ongoing and future multi-frequency B-mode projects. Of course, it's now important that we have multi-frequencies in order to cleaning up the dust component and the synchrotron foreground component. On ground, we have this polar bear, and which will be upgraded to Simon's array with 3 telescopes. And at the same site, we have this octopole, and that's upgraded to advanced octopole. And then these will be merged into the new project named Simon's Observatory. Okay. And in addition, there's some other project named ABS and class in Chile, Atacama. And another very good place is South Pole. There we have bicep 1 and bicep 2. Now we have bicep 3, KEC, and then bicep array. In addition, the large dish SPD pole is upgraded to SPD 3G. So, and these guys will be merged in 2020s with Simon's Observatory to make CMB S4. And John Carlstrom gave a nice talk 2 years ago at ICHEP 2016 in Chicago, so I won't repeat that. But this is sort of a way to go in 2020s on ground. But in addition, we have a new endeavor in Tibet, Ali CPT, and Quixote in Canary Island, and the Groundbird in Canary Island, and Cubic in Alto Corrile in Argentina. So there are many interesting projects with a modest budget, and then all the systematic uncertainties are different, so it's interesting to see all the results. The balloon, we also have Spider, IDS, Piper, LSPE, and in space, we have this Lightbird, it's a Japanese effort. So just let me just to be a little bit selfish and then touch on the project which I'm working on, Simon's Array. The first receiver system is in preparation at KK in Japan, and we expect to have a first light this year. The goal is to achieve this 0.006 or so, and we're going to have 4 bands. And as I said, the Simon's Observatory will be the further sort of upgrade and fully operation in 2021 with even more frequencies. But if you talk about the number of frequencies, actually the ultimate will be from space. So the Lightbird is a JAXA-led international mission proposal, and in phase A, it plans to observe CMB for 3 years at the Lagrangian point L2. Currently, this is the only space mission proposal in phase A in the world, and final selection is scheduled next year, and launch is expected in 2027. We're going to put this 15 bands. So with doing that, this is more or less the current B-mode power spectrum, and Lightbird is going to give us this impressive measurements. The full success is to achieve the error on R better than 1 times 10 to minus 3. So if we achieve the discovery, what will be the impact? direct evidence for cosmic inflation. That's one thing. And actually, many models predict this range, so Lightbird is supposed to detect that. And with that, you can narrow down models. And this also shed light on gut scale physics, as I said already. So this is really a new era of physics with the experimental test of quantum theory of gravity. And so this itself will arguably establish first observation of quantum fluctuation of space-time. And even now, there are some interesting endeavors in string theory community to study some top-down constraints. So it's still ongoing, but judging from recent papers, it seems it's not so easy to have value greater than 0.01 due to this super Planckian field excursions. So if you find some large number, that would be really interesting, actually. I should not say this is a string killer, but it has a significant impact on the string theory. So let me move to dark energy. So 20 years after this first announcement of the supernova type 1a, now this is a photo in a pub in Oxford. Found that now, after 20 years, you can even drink dark energy. It says without it, the cosmos would be inexplicable. That's great. It's correct understanding. The one problem is that the fraction is completely wrong. It should be 69%, as I said, unfortunately. So dark energy overview, multiple consistent observations exist, and acceleration expansion is needed, which is not realized by ordinary matter. You might say, well, okay, this is just a lambda, cosmological constant. But still very weird. It's so weird that some people say cosmo-illogical constant if you take this option. Why so small? And why now the density is about the same as the matter? No understanding. And the next logical step is to check equation of state, because so little is known. And there are several nice observational probes. And here's the future prospects. Many ambitious projects that I don't have time to go into detail, but I'm sure that these equation of state parameters will be much better constrained. So future is bright. And one of the examples shown here is a dark energy survey. And in a parallel session, there's a talk on that. And since this is not yet a real constraint on the dark energy parameter, but this is really nice new result on the cosmological parameters. For the first time, with this late universe measurement, the precision is comparable to CMB for some of the cosmological parameters, which is great. So I don't know how much time, but it's just 3. Okay, that's good. So just selected topics very briefly. There's yet another inflationary probe, which is called non-Gaussianity. In case you have, say, for instance, multi-fields, you might expect a larger non-Gaussianity. And here's a proposal named Spherex, near-infrared all-sky spectral survey submitted to NASA and now in phase A, which will give us a much better constraint on the non-Gaussianity, which will be interesting. And a little bit about neutrinos is in cosmology, because as far as I know, there's not much mention on that. So the BOSS result came out last year. Now the limit is 0.16 electron volt, which is really impressive to me. So based on the 3D million of 3D galaxies. The future prospects are even brighter using CMB lensing B mode and baryon acoustic oscillation, stuff like that. So people are really ambitious to talk about this impressive uncertainty. So even if you assume the normal hierarchy, you might have a chance to detect some finite value. And if you can really manage to go to this point, certainly you can test in a clear manner the inverted hierarchy. One thing, interesting thing I want to add is that, sorry, this one is off, but the Lightbird is not supposed to measure the B-mode lensing, but actually it provides useful pieces of information for neutrino mass measurements. By giving this tau optical depth, you can resolve the degeneracy. And then in that way, you can improve the measurement. That's another interesting synergy. A little bit about tension with Hubble constant. So we still have this tension between measurements from CMB and the local measurements. We don't know the full reason. It's about 3 sigma. So, but nicest thing is we expect further improvements in the future. So just 30 seconds about cosmology with gravitational wave detectors. Discovery of black hole mergers also stimulates cosmology. Peter already talked about the H0 measurement, and the previous speaker also mentioned this black hole, possibility of black holes with primordial origin. So I don't repeat that, but that stimulates black hole. The cosmology. And there's also a possibility of detecting first order electric phase transition. I don't know, this requires a lot of studies, but it's another interesting thing. So this is just a summary. We have a nice lambda CDM picture, well established. And now the next step important is fundamental understanding of acceleration. So that's a key. And we have lots of signature, and with the simplicity as guideline, we have a really bright future and lots of things to do. Exciting projects in experimental cosmology await us. Thank you very much.
Thank you. Questions?
Very nice talk. I'm over here. Can you comment on these couple of papers this year claiming non-zero neutrino masses from cosmology?
Yeah. So it's always not very easy to really fully understand what's going on. So again, I say that the best thing is that there are forthcoming much more precise measurements. So we should wait for that. That's what I can tell.
Another question?
Is it possible to build ground-based telescope which will be sensitive to the B mode? I mean to the low multiple range of the microwave spectrum.
How low we can go on ground? That's your question? Or?
Yes.
Yeah.
It's not possible, yes?
Down to L over 30 or so, I think it's possible. And there is an attempt, for instance, a Groundbird, which I'm also involved in, claims to access down to L of 6 or so. But you really need to beat many 1/f noise and atmospheric nuisance, stuff like that. So, but small-scale ground-based experiment is a sort of an experimental experiment. You try, learn, and then upgrade. So that's a current style, at least, as long as the small-scale one is concerned. Now, CMBS4, even the Simons Observatory, is getting big. It's a Simons Observatory is 6 million project, so probably you are losing that freedom. But for low L, you have still that.
Pollution becomes bigger on large scales, yes? Pollutions.
Sorry?
Pollutions in atmosphere. Why we...
Yeah, exactly, right. Kolmogorov, if you think about the Kolmogorov spectrum, it's,
okay.
yes. So it's not easy. By far, I believe that by far the space measurement is much, much better for lowest L.
Thank you. I think we should move on. Let's thank Sashi again. So, to end the session, we have Andre Kunin speaking about high-energy cosmic rays.
Good afternoon. A short disclaimer before I start my talk. In fact, this talk was prepared by Sam Ting. I modified it just for my taste. So if you see some inconsistencies or inaccuracies, please blame me. So neutral part of cosmic rays like neutrinos and gamma rays were presented earlier in the plenary sessions. So the subject of my talk are charged cosmic rays, and we really have a lot of talks presented in the parallel sessions. So we have heard from ground-based experiments, Pierre Auger Observatory telescope arrays, very interesting result about possible anisotropy of extremely high energy cosmic rays. However, the focus of my talk is this range. So here you see the spectrum of all particles from 1 GeV to 100 exa-electron volts. And the range from 1 GeV to about 10 TeV is covered by 4 experiments which were discussed in the parallel sessions: AMS, CALET, DAMPE, and ISS CREAM. And the physics, in fact, of all the charged cosmic rays is very rich. So it spans from sub-GeV range, where we have solar physics, up to about 100 EeVs, where we have extragalactic sources. So I will be reviewing 4 experiments, which are space-borne cosmic ray experiments, which are in operation, of which AMS is the only magnetic spectrometer in space. It's also the most mature experiment, so it's well in its 8th year of operation, whereas CALET and DAMPE just finishing their 3rd year of operations, and ISS CREAM just started a little under 1 year ago. The building of a space-borne experiment is actually a very long-term endeavor. So it took 600 physicists about 17 years to construct AMS. Here you see a map of contributing institutions, and I want to take this chance to acknowledge the contribution of our Korean colleagues, Professor Dong-Chul Son and En-Sok Seo, to this experiment. AMS is a TeV precision accelerator type spectrometer in space, and the unique features of these experiments are 2. First, ability to distinguish positive and negative charge, and second is high level of redundancy of the measurements. In AMS, the particles and nuclei are identified by their charge, energy, momentum, but throughout this talk I will be using a lot rigidity, which is actually the ratio of momentum to charge. Well, in order to achieve the precision measurement of cosmic rays, in AMS there are 5 detectors outlined in this slide. On top, transition radiation detector, identifying electrons, positrons, measuring charge of nuclei, silicon tracker to measure charge and momentum, and together with magnet to separate positive and negative charges. On the bottom, we have electromagnetic colorimeter to measure energy of electrons, positrons, also to distinguish them from heavier particles. We also have time of flight and reach to measure charge and velocity of the particles. And as I mentioned already, these critical parameters of every particle is identified independently by several detectors. So in my talk, I'm going to cover 4 topics. First, studies of light, antimatter, like positrons, antiprotons, complex antimatter, charged nuclei, and also some practical applications. It was noticed a long time ago by Turner and Milchik that, in fact, we have to pay attention to study rare cosmic ray species, like light antimatter. For instance, to test fundamental interactions. For instance, dark matter annihilation will produce this light antimatter, and which can be easily detected on top of very small background from collision of ordinary cosmic rays. And conversely, for ordinary matter, this measurement becomes extremely difficult. So the measurements in space are, in general, very difficult. So here you see the electron and positron spectra measured before AMS. And in fact, looking at this plot, I do understand why Particle Data Book still claims that all the cosmic rays are well described by a single power law. So what you see here is flux of these particles, electrons and positrons, multiplied by 3rd power of energy, just for display purposes. And here are newly released AMS measurements. So based on about 30 millions of electrons and positrons. So what one can see here on this plot, that the spectra are very different in magnitude. So here the positron flux is multiplied by factor 10, but also in their energy behavior. And the most peculiar feature is actually behavior of the positron flux. Let's see why. So if we compare with contemporary models of cosmic rays, basically there is a reasonable agreement at extremely low energies. However, starting from about 10 GeV, there is a departure from this predicted behavior. The spectrum becomes flat. Next, there is a hardening of the spectrum until the spectrum reaches its maximum at around 300 GeV. And then there is a drop-off. This type of behavior is very well consistent with a contribution of new source of high-energy positrons, like, for instance, dark matter. And indeed, if we make just comparison of dark matter models with our observation, there is very nice agreement. Here you see a model which is based on this publication. However, dark matter is not the only model which describes our data. There are many attempts, and just to mention, we have over 2,000 citations for our positron and antiproton results. So all the new models which try to describe the observed behavior can be categorized in 3 big classes. Models which deal with particle origin of this excess, like dark matter, astrophysics origin, like pulsars or supernova remnants, and specific propagation of cosmic rays. So one has to notice that actually all these models, they really describe trends of a single measurement. However, they fail to describe simultaneously several precision measurements. And this situation is actually shown on this slide, where you see theories struggling against incoming waves of new precision data. In fact, this painting was shown by one of the theorists, Igor Moskolenko of Stanford, last year. But this basically a good representation of current situation with precision measurements and theoretical understanding of it. So to give you a few examples, I want to show a few models. One which is based on astrophysical sources, supernova remnants by Subir Sarkar. So there are quite a few parameters in every model. So what happens in this particular model, that tuning parameters to positron spectrum, we can achieve reasonably good agreement. However, with that set of parameters, there is quite a bit of discrepancy for the measurement of boron to carbon fluxes. And conversely, if the parameters are tuned to boron to carbon ratio, there is a discrepancy with positrons. In order to show the next type of model, I want to introduce a positron fraction, which is a ratio of positron flux to the sum of positron and electron fluxes. So here you see new AMS measurements together with many previous measurements. And the model by Kozik of new propagation model. So here you see the AMS dots in gray, the model pink band, and at first glance there is a reasonable agreement. However, if one checks the underlying assumption of this model, there is quite a bit of discrepancy. So here is the assumption of the model, and here are experimental data. So it's fair to say that at this moment, the observed features of AMS positron data cannot be explained by standard propagation model. There are also quite a few measurements coming from other experiments. I want to highlight a measurement done by HAWK experiment, High Altitude Water Cherenkov Gamma Ray Observatory. So they published last year, at the end of last year, a paper in Science, saying that the observed flux of photons is not sufficient to explain the large excess of positrons if they come from nearby pulsars. So here you see 3 sigma band corresponding to their measurement. So what other experiments can do in this field? So of course they cannot distinguish positive, negative charges, but what they can do is to measure a combined flux of electrons and positrons. So here you see AMS together with Hess and Khaled. So what you see, there is reasonable agreement up to 1 TeV. Then, well, agreement actually stays there all the time. But at 1 TeV, there is yet another feature. There is change of the spectral index. So I want to put also other data by Dampe and Fermi-Lat. So they all observe the very same feature, a change of spectral behavior at 1 TeV. However, there is a discrepancy in the range from 100 to 800 GeV. And this is still something to be worked out. Of course, after having a look at positrons, the question is, do we see similar features in antiprotons, for instance? And 3 years ago, before publishing AMS results, it seems, yes, we see similar features. So here is prediction from the collision of ordinary cosmic rays for secondary antiprotons. And here is contribution of 1 TeV dark matter model. However, since then, there was a lot of theoretical development in order to understand production mechanism and actually compute the, precisely compute the details and get estimates of the new flux. So the basic trend is all predictions for secondary antiprotons, they moved up to become almost consistent with AMS data. However, if you look closely, we still have some tension at extremely high energies, around 500 GeV, or at lower energies around 10 GeV. And in fact, there are a few papers claiming that, in fact, this excess can be attributed to dark matter of about 50 GeV. However, regardless of models, there are quite a few very interesting features in the data. So if we compare antiprotons and protons, they exhibit a very similar behavior in a very wide range. So one cannot say the same for positrons and electrons, which are essentially very different functional behavior. But what is even more surprising, that antiprotons, positrons, and protons from 60 GeV to about 500 GeV exhibit the very same behavior, and electrons stand apart. I want to change subject, so I want to review briefly the cosmic ray nuclei, namely helium, carbon, oxygen. These are primary cosmic rays because they are produced at their source and travel through space before they are detected by space experiments. So they carry information about their sources and the history of travel. And again, this measurement is quite difficult. So you can see here the measurements for helium, carbon, and oxygen as a function of kinetic energy per nucleon before AMS. And here you see AMS data. So what one can learn looking at this plot. So this is a flux multiplied by rigidity to 2.7 power. So up to 200 GeV, there is one power law, and then there is a smooth transition to another power law. And this is quite unexpected. So this is a smooth transition which happens at around 200 GeV. So the question is, do secondaries, namely nuclei which are produced in collision of primary cosmic rays and therefore carry information about history of the travel and properties of the interstellar media. So these secondaries, in our case, are lithium, beryllium, boron. And if we compare the observed behavior of secondaries, we do see that actually they change their behavior at around 200 GeV, but this behavior in general is distinctly different from the primary cosmic rays. The dynamics of this transition at around 200 GeV is actually a very interesting subject, because if we take a ratio and compare the ratios for secondaries to primaries, to carbon in this case, and to oxygen in this case, we see that hardening for secondaries is actually much more pronounced. So for instance, overall, combining all these 6 measurements, secondary to primary can be parameterized as a power law, which in fact from 200 to 3000 GeV is quite different from that of from 60 to 200 GeV. And there is no really explanation yet for this observation, but hopefully it will be worked out in future. So nitrogen is, as one can see, is kind of a combination of primaries and secondaries. And indeed, if one approximates a primary component by oxygen, which is pure primary, and secondary component as boron, which is pure secondary, one can see that there is very good agreement of this linear combination for nitrogen, so which allows us to measure the ratio of primary nitrogen to primary oxygen irrespective of the features of the propagation directly at the source. So the result of this measurement is quite interesting, because if one takes a ratio nitrogen to oxygen or carbon to oxygen, and these are the AMS measurements, and compare with the abundances, the ratio of abundances in the solar system, they are quite different, and quite different in actually opposite way. So now a few words about practical applications. Actually, our low energy data are of a lot of interest to NASA for interplanetary travel. And here you see a brief summary of the results for protons and helium as a function of rigidity for different plots and as a function of time for all AMS data taking period. You see that actually there is very good correlation between protons and helium time dependencies. It's not the case for different charges, opposite charges for electrons and positrons. This paper is to appear in PRL very soon, actually, well, hopefully this week. And actually what the observation of this paper is that there is a time lag between observations, which is related, for instance, to the number of sunspots and the fluxes of galactic cosmic rays, positrons and electrons. And this time lag rigidity dependent and is about 1 year, which is quite important for planning this interplanetary space travel. So a few words about the future. So here I say for AMS. So here we are actually working on complex antimatter. I will give you a few results on positrons and dark matter, and isotropy as another probe for dark matter and high Z cosmic rays. So in AMS, since we are able to identify the sign of the charge, we are also very much interested in detecting helium with negative charge. And in fact, this type of events are coming at a regular rate. So this event was presented already on several occasions in different conferences. So the momentum is about 30 GeV. The charge is -2, and the mass is 2.93 GeV, which is quite consistent with the mass of helium-3 of 2.8 GeV. The charge is negative, and we don't really expect these events at all, because predictions of current models actually are about 2 orders of magnitude below, and only models which include dark matter can reach the rate at which we observe these events. But that's not the end of the story, because in addition to helium-3 events, we also observed several anti-helium-4 candidates. And in fact, we have 2 events like this. So the rate of these events is extremely low. It's about 1 per year, or about 1 per 100 million of ordinary helium events. Of course, before we announce discovery, we need to ensure that these events are not a background. We also look at anti-carbon and anti-oxygen, and here we explore the very same approach as for anti-helium. So we enlarge acceptance to get more carbon and oxygen events, and by the end of the space station, we plan to collect about 100 million carbon and oxygen events to study anti-carbon and anti-oxygen. We also plan to improve on the precision of the drop-off in the positron spectrum. At the moment, despite the eye-catching effect, this drop-off, the real effect is about 2 sigma, and by 2024, we plan to put 1 more point and achieve a significance of about 5 sigma. Together with an isotropy measurement, because dark matter is more isotropically distributed. However, astrophysical sources like pulsar will imprint a higher anisotropy on the arrival directions of energetic positrons. compared to dark matter. And by 2024, we plan to achieve the 3 sigma significance and to exclude or to observe pulsars. Well, for studies of high Z cosmic rays, we have all 4 experiments: AMS, CALET, DAMPE, ISS CREAM, which plan to contribute. So here, we are addressing few issues. The probe different galactic distances, because different particles, different charges, probe different distances. In fact, what you see here is a kind of view of our galaxy from the top, and here is the range which we can achieve with different nuclei. We also plan to have data from all 4 experiments for higher charges from 9 to 28. What is interesting here is to see the energy dependence, and of particular interest is the flux break at 200 GeV. Also, the measurements of aluminum, chlorine, and manganese spectra will precisely establish the age of cosmic rays, because all these isotopes are radioactive clocks. And also, this gives us information about different production mechanisms of all these nuclei. Light nucleus, for instance, up to lithium, they are mostly produced during Big Bang nuclear synthesis. The other nuclei up to iron, they are produced by stellar nuclear synthesis, and other heavier particles by supernova. So let me conclude. So most of the results which I presented today are unexpected and require much improved accuracy of theoretical predictions. There are several large-scale detectors in space right now to study high-energy charged cosmic rays, and AMS of them is the only magnetic spectrometer. So we really need more new precision data to uncover the origin of many effects which are observed and so far unexplained. Thank you.
Thank you. Do we have one burning question before the coffee break?
Can I?
Please.
Do you know if CALET and DAMPE could exploit techniques like Fermilab to distinguish electrons and positrons?
Well, in principle, yes. Here there is one caveat. So this technique doesn't really work well for higher energy positrons. Like starting from 300 GeV doesn't work at all. And this is the most interesting region.
But at least the Fermilab has already some spectrum.
Well, yes, in principle, yes. But if you look at Fermilab systematic errors in this region, they are quite significant. So, you know, it's difficult. It's a tough measurement.
But could it help somehow to improve the statistic, increase the statistics, etc.?
I don't think these experiments can compete with precision achieved by AMS, because, well, antiprotons is actually a much better example. So we have over 3,000 antiprotons above 100 GeV, whereas before there were only 3 events above 100 GeV, and none of these calorimetric experiments reported any antiproton observation. So
Thank you. We have one other important question.
Quick question. So in terms of the charge identification for positrons especially, it's pretty high momentum and the size of the spectrometer pretty small, and electron flux is pretty high. So you have to be able to identify charge with high precision. So how you're doing that, and what's the numbers here?
Yes. In fact, the field is about 1.5 kilogauss, but the baseline is not really small. It's 3 meters. So that's why actually our maximal detectable rigidity is for protons, for charge 1 particles, is around 3 GeV. Oh, 3 TeV, excuse me.
Thank you. So our coffee is getting cold. Let us thank all the speakers again.